uranium is really made. It starts half a kilometer underground in northern Saskatchewan, Canada at the Cigar Lake mine. This is not a normal mine. The ore here contains up to 20% uranium. Most mines celebrate at 2%. Cigar Lake is 100 times richer than average. But there is a catch. The uranium sits beneath sandstone completely saturated with groundwater. Imagine trying to dig a tunnel while Niagara Falls pours through your ceiling. The solution sounds like science fiction. Engineers freeze the ground. 200 steel pipes are drilled into the rock, each one taking 8 days to install. A freeze plant on the surface chills calcium chloride brine to minus 30 degrees Celsius and pumps it through these pipes. The water in the sandstone turns to solid ice, creating frozen walls that hold back millions of gallons of groundwater. An ice fortress underground. Everything about the mining is remote controlled. Operators sit in sealed booths 50 meters away, guiding drills with tungsten carbide bits, one of the hardest materials on Earth, second only to diamond. A mechanical reamer chews through the rock. When the uranium ore breaks free, it tumbles into collection chambers. Radiation meters spike. Fresh air cycles through the mine every 20 minutes because the radiation from this ore is strong enough to cause cellular damage. The ore is pulverized by hydraulic hammers, ground into sand mixed with water, and pumped to the surface as radioactive slurry. By the time it reaches the surface, what was once solid rock has become a thick liquid heading for the mill. Now why? At the mill, the slurry meets its first chemical transformation. Sulfuric acid floods over the crushed ore, dissolving only the uranium while the worthless rock minerals sink to the bottom. Think of it like this. If you had a mixture of salt and sand, you could dissolve the salt in water and filter out the sand. That is essentially what happens here, except instead of water, they use acids powerful enough to eat through steel. The uranium-bearing solution is drawn off, purified through solvent extraction, and then roasted at 1085 degrees Celsius. That is hot enough to melt copper. The temperature has to be precise. Drift by even a few degrees, and millions of dollars of uranium are ruined in minutes. After 4 hours in the furnace, the uranium emerges as a dense black powder called yellowcake. Despite the name, yellowcake is actually black or dark brown at this stage. It is packed into 55-gallon steel drums, each one sealed, stamped with inspection marks, and labeled with radioactive hazard warnings. Each drum contains enough potential energy to power a small town for months. But right now, that energy is still completely locked away. The drums are loaded onto specially designed transport trucks, not ordinary trucks. These are rolling vaults with reinforced steel walls, radiation shielding, and locking systems designed to survive highway accidents. The route is classified. Even the driver cannot tell his family which roads will be taken. Radiation badges are checked every 3 days. You are about to see where this process gets genuinely dangerous. What happens next is the reason uranium enrichment facilities are among the most heavily guarded buildings on Earth. The black powder from those drums is about to become one of the most corrosive substances known to science. Inside the conversion facility, the yellowcake undergoes a series of chemical reactions that sound like they belong in a supervillain's lab. First, it is dissolved in nitric acid to create uranyl nitrate. Then it is purified through solvent extraction using tributyl phosphate. Then it is reduced, hydrofluorinated with hydrogen fluoride, and finally fluorinated with elemental fluorine gas at 550 degrees Celsius. Bright flames erupt through observation ports. The pressure gauges dance into the red zone. What comes out is uranium hexafluoride, or UF6, a gas so corrosive it can eat through your skin and dissolve bone. The entire facility is built from special nickel alloys and aluminum, the only materials that can survive UF6's hunger to corrode. But here is why this terrifying process is absolutely necessary. Natural uranium is 99.3% U-238 and only 0.7% U-235. U-235 is the isotope that splits and releases energy. U-238 is weight. They are chemically identical. You cannot use magnets. You cannot use chemical reactions. The only difference between them is that U-235 is about 1% lighter. Imagine trying to separate identical twins who differ in weight by just 3 pounds out of 1,000. You would need a machine that can feel that tiny difference. Uranium hexafluoride is the only uranium compound that becomes a gas at a reasonable temperature. It sublimes at just 56.5 degrees Celsius. As a gas, physics can finally separate the useful from the useless. The UF6 is cooled, drained into 14-ton steel cylinders, and allowed to solidify over 5 days before shipping to the enrichment plant. Day 40. The centrifuge operator arrives before dawn at a classified enrichment facility. What they walk into is a maze of thousands of centrifuges, each one spinning inside reinforced stainless steel containment vessels. Each centrifuge rotor spins at 50,000 to 70,000 revolutions per minute. That is almost twice the speed of a fighter jet engine. The rotor walls are moving at 400 to 500 meters per second. If a centrifuge fails, it does not just stop, it disintegrates. The containment vessels are there for a reason. Gaseous UF6 is fed into each centrifuge. The spinning pushes the heavier U-238 to the outer wall, while the slightly lighter U-235 concentrates near the center. But one pass is not nearly enough. The gas flows through cascade after cascade of centrifuges, each one nudging the U-235 concentration up fractionally, from 0.7% to 1%, from 1% to 2, from 2 to 3, from 3 to 5. It takes about 8 separative work units to produce just 1 kilogram of 5% enriched uranium. A single 1,000 megawatt reactor needs about 140,000 separative work units per year. This is why only 6 nations on Earth operate commercial enrichment facilities. The engineering, the precision, the scale, it is beyond what most countries can achieve. When the target enrichment level is reached, the UF6 is converted back into uranium dioxide powder through either a dry or wet process. In the wet process, the UF6 is heated until it vaporizes, hydrolyzed with water, precipitated with ammonium hydroxide, and then calcined with hydrogen to produce microcrystalline UO2 powder. Every grain must meet ASTM specifications for stoichiometry, impurity levels, density, grain size, and pore morphology. A single deviation could cause cladding stress, fission gas release, or a reactor performance failure. Now the powder becomes physical. Under several hundred megapascals of pressure, the UO2 powder is pressed biaxially into green pellets about 10 to 13 millimeters long and 8 to 13.5 millimeters in diameter. Each one weighs roughly 10 grams. Quality inspectors check every pellet for dimensional accuracy, density, and enrichment lot identity. A cracked green pellet or a density variation could cascade into a catastrophic failure inside a reactor. The stakes are that high. The approved pellets slide into sintering furnaces running at 1600 to 1750 degrees Celsius in an argon-hydrogen atmosphere. For 24 hours, the pellets shrink and densify as pores close and grain structures form. After sintering, ceramic grinders machine each pellet to its exact final diameter. Any UO2 removed during grinding is recycled back into the pelleting circuit. Nothing is wasted. But now comes assembly. Zirconium alloy tubes, about 4 meters long, are loaded with roughly 300 sintered pellets each. Zirconium is chosen because it is exceptionally resistant to heat and corrosion, and critically, it allows neutrons to pass through freely during the fission reaction. The tubes are flushed with helium, pressurized to several megapascals, and sealed with welded end plugs. 37 fuel rods are bundled into a structured fuel assembly. Each assembly is weighed with precision to verify the exact uranium content. Technicians perform final inspections using X-ray machines and ultrasonic scanners that can detect flaws invisible to the human eye. The assemblies are then loaded into transport containers built like armored coffins, designed to survive plane crashes and direct missile hits. They travel by specially designed trucks with armed escorts, every shipment tracked by satellite, every route classified, every delivery a matter of national security. At the nuclear power plant, the reactor vessel opens to receive its new fuel. A steel cathedral 40 feet tall with walls 8 inches thick. Robotic arms guided by operators in radiation suits carefully insert each assembly into the reactor core. Control rods withdraw, neutron levels climb, and then the first U-235 atom splits, then another, then billions. The chain reaction generates immense heat, carefully regulated by automated safety systems. Water turns to steam. Steam drives turbines the size of 20-story buildings, spinning at 100 revolutions per minute. Each turbine drives a generator, producing over 750 megawatts of electricity, enough for 500,000 people. After roughly a year, the fuel assemblies are spent. They are so intensely radioactive that they must be submerged in cooling pools 26 feet deep for at least 10 years. More than 700,000 spent fuel rods currently rest at the bottom of these pools worldwide. Remember that pellet from the beginning, the one that weighs 10 grams but holds the energy of a ton of coal. nature made it 99.3% useless. Humans spent 70 years building the most extreme industrial process on Earth just to concentrate that 0.7%. Underground ice fortresses, acids that eat steel, gas that dissolves bone, centrifuges spinning faster than fighter jets, furnaces at 1700 degrees, all of it to unlock what was hiding in plain sight. The most energy-dense material we have ever produced, pulled from ordinary